So let's talk about what we were talking about last week, nuclear chemistry. So this is kind of everything we did last week, right? We talked about all of our alpha, beta, gamma, positron, and electron capture. And what we're going to talk about today is kind of why do different nuclei choose different ones, right? So we went over the individual, like what is alpha, what is beta, what is gamma. Now we're going to talk about, like today, why one atom does an alpha and the other one does a positron, like why? And it has a really big thing to do with this NZ ratio, the neutron to proton ratio. And so you're going to see here, an alpha decay increases the ratio, and we're going to talk about this ratio in just a second. A beta decay decreases. Gamma does nothing, so we're not going to talk about gamma today. Positron increases, electron increases. So in general, we're looking, does it increase or decrease this N to Z ratio? And this has to do with the stability of the nucleus. Right, and this NZ ratio against like neutrons to protons, right? Neutrons, Z is the atomic number, protons. Okay, so first of all, what causes the nuclei to decompose anyway? Well, there's this thing called a strong force, and a strong force is what holds the nucleus together. So it holds the pieces of the nucleus together, the pieces that are smaller than protons and neutrons, and it holds together proton-proton attractive forces, proton-neutron attractive forces, but there's also repulsive forces in there also. So the strong force is a very strong attractive force. It only acts over a very short distance, the nucleus. And again, it binds that nucleus together. Now, if the repulsive forces, which this is like way beyond what we're going to talk about, but if the repulsive forces in that nucleus are greater than the attractive forces of that nucleus, then that means the nucleus will be unstable, and then the nucleus will begin to degrade. And when it does that, it'll either emit matter, beta, alpha, right, or some kind of energy, radiation, like gamma radiation, etc. So a particle or radiation, it's usually a combination, will be emitted, so it then has more attractive forces than repulsive forces, hence a stable nucleus. So the thing that holds the nucleus together, that's called a strong force. Okay. So now, talking more about that NZ ratio. So the ratio of neutrons to protons, again, this is what kind of leads to the stability of the nucleus. If the ratio is too high, it's unstable, and the neutrons are converted to protons via beta decay. If the ratio is too low, then the protons are converted to neutrons, either positron emission or electron capture, right? Or alpha decay, but not as commonly. Okay, so let's look at what's stable and what's unstable. So this is called either the belt of stability, the valley of stability. It has all these names. And so you can see here, the green is kind of, that's our valley. See the green here? That's like our valley or our stability belt. It has a couple of different names. And so here's the number of protons, here's the number of neutrons. So we're just looking at the ratio of neutrons to protons. And so you can see here, here's when protons equals neutrons, which is a ratio of 1, right? And so you can see here kind of like below 20, they're pretty much equal, right? That's a pretty equal, pretty much the ratio is about 1. Now again, it's not perfect. So when the ratio is about 1 for atomic numbers 1 to 20, right? So this is from 1 to 20, all the way up to calcium, the stability is about 1. Now, when we're going from calcium all the way to 40, which is zirconium, so this is like period 4 and 5, the stable ratio is about 1.25. And we're going to talk about what this means in just a second. When we go from 40 to 80, so this is like periods 5 and 6, 40 to 80, The stable ratio is about 1.5, and above 83, there's nothing stable, right? So that was polonium, our number above 83, so starting at 84. So polonium, everything's unstable after polonium, and everything's going to degrade via some sort of transmission. Okay, so remember, if the ratio is too high, so if it's above the, so here's our, I'm just going to draw it like this. So it's like an uneven valley of stability, okay? So if your ratio is too high, meaning you're above the valley of stability up here, then it's going to try to, the nucleus, in order to be stable, is going to try and decrease the ratio so it can get down to that stable point. Now, in order to decrease the ratio, it's going to undergo beta emission, because remember beta, or usually beta emission, not always, because remember beta increases protons, Z, right? Actually, I'll write protons because I don't want to like put too many letters in here. And then at the same time, it decreases neutrons. So it increases that NZ ratio, or decreases the ratio. I can write today, right? So it reduces it. So it goes from here down to there. Now, if the ratio is too low, right? If it's too low, then it's going to undergo either more likely positron emission or electron capture. So we can try to get up from here, up closer to the actual valley of stability, or the belt of stability, depending on which book you're reading. Okay, so let's try to use this. Okay, magnesium 22. So you look at magnesium, 12 protons. Well, that's supposed to say, I'm going to put P, 12 protons. I think I have this on here, right? Yeah, there we are. 12 protons, right? 10 neutrons, 12 protons. So our NZ ratio, neutrons over protons, is 0.83. Now, this is, remember, magnesium is number 12, right? So it's between the 0 to 20 level. And remember, from 0 to 20, the most stable isotopes had a ratio, an NZ ratio. So let's go to 20 here. Actually, we're at 12. Oh, it's a 1-to-1 ratio, right? So this should be 1 for a stable nucleus, but it's 0.83. So this means our ratio is a little low, right? We need to increase our ratio to make it closer to 1. Remember, to increase the ratio, that's positron emission or electron capture, right? So let me just go back. I'm going to go show this picture again of where you can see this. This, right? We need to increase our N to Z ratio, electron capture, positron emission, right? This little picture here, very handy. And sometimes alpha, it's just not as common. Alpha's a little dramatic because it makes such a huge change. But there are alpha, it's just not as common. Okay, so let's look at our magnesium again. Okay, so again, our stable ratio should be about 1, but we're at 0.83, so we're too low. And so because it's low, we want to convert our protons into neutrons. So that's positron emission or electron capture, right? Okay, let's try another one. Krypton 85. So the question is it stable and is it radioactive? So just really quickly, I want to do one here just so you can see. Let's do carbon 12, right? If you did carbon 12, right? So carbon 12 has 6 protons and 6 neutrons, right? If you do your N to Z ratio, that's 6 over 6. That's a ratio of 1. Carbon's atomic number is 6. So it's between the 0 to 20, which means its ratio should be 1. Its ratio is 1. Carbon-12 is stable, therefore not radioactive. See how that works? I wanted to show you one that's not radioactive so you can see how this works. Okay. Obviously, this one I'm showing you is going to be radioactive. Okay, so let's try krypton, 85. So krypton, 36 protons, and 85 minus 36, 49 neutrons. Okay, 36 protons, 49 neutrons. So remember, krypton is 36. So if we want to go back here, it's 36. So it's between 20 and 40. So a stable non-radioactive nucleus, one that doesn't need to degrade, is going to be 1.25. That's what we're looking for, 1.25. Okay, so we want 1.25, or actually, you know what? I'm just going to write stable is 1.25. So we do our N to Z ratio, 49 over 36, and we get 1.36. Okay, it's too high. 1.36 is too high. So if it's too high, this is going to be beta decay. Right, so remember, if the NZ ratio is too high, it undergoes beta decay, right? That is going to reduce our N to Z ratio, right? And again, you can find that, you can either do the beta decay and actually see it, or you can just remember beta decay, what it does is it increases a proton and at the same time decreases a neutron. Okay, which would decrease our, or at least get us closer to 1.25. Okay, so let's see. I think I solved this. I'm sure I solved this. Oh yeah, here we are. Here's our number of neutrons. Here's our N to Z ratio. It should be about 1.25, right? Remember, 1 is always perfect, but only ones that, there's very few that do that. So 1.25. And so this is greater than 1.25, so it undergoes beta decay. And if we actually look at that beta decay, we can see indeed it ends up being rubidium, right? And just a little FYI, this is actually a byproduct of nuclear fission, and this was released in the atmosphere when they were testing atomic bombs in the 40s to the 60s. Just a little FYI. We're going to be talking a little bit about this. Oh, I also want to remind you, when you're reading your book for this chapter, go to the online link that I gave you, right? It's called OpenStax. It is so interesting. I think it explains things in more detail than your book and way more interest. It tells you about all the different types of bombs, where they're used, how they're made, when they were done. So it's kind of a little history lesson too. Okay, so there are certain magic numbers. So you know with like electrons, like the magic numbers of electrons would be the same as, you can't see this, the same as the noble gases, right? So 10, 18, 36, 54, 86, those are the stable. There's the same type of thing with the nucleus. So the actual numbers of protons and neutrons affect the stability, and most stable nuclei are even numbers of protons and neutrons. Now, the reason for this has all to do with the strong force. We're not going to talk about the reasons because they're so far beyond what we do. We're not going to talk about those. Only a few stable nuclei are odd numbers. So we have these things we call the magic numbers. So just like you have stable atoms when it comes to reactivity, you also have stable atoms when it comes to nuclear stability, right? And these are our magic numbers. When either the protons or the neutrons are 2, 8, 20, 28, 50, or 82, or the neutrons are 126, right? And then these ones, again, these are what we call our magic, numbers. And you're gonna see, we're gonna do some like practice with these. So like, for example, tin. Sorry, I'm looking at my periodic table. Tin is like, what number is it? 50. So tin has an atomic number of 50. And antimony has an atomic number of 51. This one has 10 stable isotopes. This only has 2. Right? And it's, again, tin just happens to be one of those magic numbers. So it has more stable isotopes. Now you can see the proton to neutron if it's an even to even. So that means even number of protons, even number of neutrons. There's 157 stable nucleides, right? Even odd, 53. That means an even number of protons, an odd number of neutrons, way less. Odd number of protons, even number of neutrons. By the way, you don't need to know this. I'm just showing you the differences, 50. But if there's an odd neutron and odd proton, there are only 5 total stable nucleides on the entire periodic table. So this is very rare, right? And again, so if a neutron or proton has these numbers, 2, 8, 28, 42, or the neutron is 126, right? We don't have an atom that has an atomic number 126. These are our magic numbers, which means we're going to have stable nuclei, non-radioactive. Okay, so now we're going to talk about a decay series. So a decay series is when one nuclide decays into another, which then decays into another, right? So you have your parent, daughter, and we keep going. So the daughter nuclide is also radioactive. So all the radioactive nucleides that are produced after one another until we get our stable nuclide is called a decay series. So you keep going all the way till you get to the stable one. Now, I'm not going to make you count these decays. I'm going to show you one right now, but you can actually kind of figure it out. So you can count the number of alpha and beta decays, and from the mass number, you subtract 4 for each alpha, and for the atomic number, 2 for each alpha, and add 1 for each beta. Now you're going to see what I mean here on this next page. So this is the decay series for uranium-238. And so on this decay series, very, very well known. Again, here's our protons, here's our neutrons right here, protons and neutrons. Actually, that actually helps me. I don't know if I can write on it here. I can't. But you see how, you can see the hand. See the kind of bluer, the longer ones are alpha and the shorter ones are beta. So you can actually look at this. So this is, sorry, I can't write on my screen. Try again. Well, no, just fix my pen. So you can see the first one's an alpha decay. The second one's a beta, alpha. So instead of writing all of it out, sorry, I'm trying to fix my pen. There we are, alpha, beta, alpha, alpha. And now it could, those aren't 2s, those are alphas. It could go alpha or it could go beta. It could go alpha, beta, alpha. It could go beta, alpha, right? There's a lot of variety here, right? And we never know which one it's going to do. But as you can see here, for each alpha decay, so if you're starting at uranium-238, for each alpha decay, just subtract 4 from the mass number for every time you see an alpha decay. So you take subtract 4, subtract 4, subtract 4, subtract 4, subtract 4, right? 4, and again, this is the mass number. For the atomic number, you subtract 2 for each alpha and add 1 for each beta. So from the atomic number. So uranium is what, 92, I think? Yeah, uranium is 92. So from 92, you would subtract 2, subtract 2, subtract 2, subtract 2, subtract 2, and there's 2 betas, add 1, right? So instead of actually like writing out every going, like if I wanted to go, hey, from uranium, after I go through 1, 2, 3, 4, 5 alpha decays and 2 betas, what do I get? So you could actually write the equations for 5 alphas or 2 betas, or you can just subtract, right? So here's, at this point, we'll be at polonium. And now, I mean, it could go here, it could go here, or any other combination. You saw, like, we could do this over there, or we could do this. I mean, there's so many different combinations it could go under. You do not need to memorize this. You just need to be able to recognize it and use it. This is a decay series. By the way, for it to go from here all the way down here, it's like 1 billion years. It's rather slow. When it makes it stop right about here, this causes lung cancer, right? This one's very bad. This radon right here, it's actually found naturally in rocks, and it's from the decay series from uranium down to lead. Again, this takes about 1 billion years, but this is, if you've ever heard of people getting lung cancer and they've never smoked or anything, a lot of times it's due to radon, which is commonly found in ground. It's found in our ground, not as much as ours, down in the south. It's actually very prevalent. Okay, and we'll talk more about that. Probably not today, probably tomorrow, or sorry, on Wednesday. Okay, so now let's talk about the rate of radioactive decay. So how fast does this happen? So I told you from here to here is 1 billion years. How do we figure that out? So that's what we're gonna do right now. So again, it was discovered that the rate of change and the amount of radioactivity is constant for each isotope, so it never changes. So a radioactive uranium, we just talked about a uranium-238, decays at the same rate no matter what. You can heat it, you can increase the pressure, you can do whatever you want to it, nothing's going to change it. Right, so it decayed at a particular time and a particular amount, and there was nothing you could do to change it. It was constant. And what's used to count this is called a Geiger counter. You can read more about it. It just counts the amount of decays per minute. And again, increasing temperature didn't change it. Pressure, nothing changed it. So if you remember from kinetics from last semester, right, your last experiment in Chem 219, what you did is you increased the temperature of the reaction. Do you remember the reaction where you like mixed this and this and then it turned blue? When you increase the temperature, it went so much faster. Or when you decrease the temperature, it went so much slower, right? Well, with these types of reactions, temperature doesn't change it. This means that it is not a chemical reaction, right? It's not a chemical reaction. This is a nuclear reaction. Okay, this is going to use first order rate laws. If you're like, I don't remember first order rate laws, it's okay. We're going to talk about them right now. So kinetics, by the way, is on your final because we're going to be doing it right now. So this is still your rate constant. Rate constant. This N is the number of radioactive nuclei. So it's usually in like, it's usually in grams, but it doesn't necessarily have to be in grams. It can be in atoms. It can be any amount. This is the shorthand for the half-life for a first order rate law. And then this is the integrated rate law. Remember? You're like, no. So this is the integrated rate law. Again, you're not going to need to memorize these two. I will give these to you. We're going to practice using these with our rate laws, with our kinetics and our radioactive nuclei in just a second. So the shorter the half-life means the faster it degrades. So a half-life is just the amount of time it takes for something to degrade 50%. So 50% is gone at each half-life. And we're going to look at some of these in just a second. So the faster it degrades, we call it hotter, because the more emissions will occur in a shorter amount of time. So here's just some examples of half-lives and the type of decay that occurs. So for uranium to get down to that stable lead, a billion years. I also want to show you, so uranium, we're going to talk about, uranium is what we use in nuclear power, right? That's what we use in nuclear power plants. And if you've heard any of the issues with nuclear power plants, which we're going to talk about nuclear power later today, but if you've heard any of the issues, a lot of the issues is, how do you store this? How do you store it? Because it's a billion years until it gets to a stable nuclei, right? Before that radioactivity, it has to go through all of this before it gets stable, right? All of these are unstable radioactive nuclei. All of these, every single one is a radioactive nuclei. And it takes a billion years for it to get to here. So a big problem with nuclear energy is, where do you store it? Because it needs to stay there for a billion years, right? Big issue. We have not found a solution yet. One solution was take it to Nevada in a mountain, dig the mountain out, put it in the mountain. No joke, look it up. They're trying to revive that one. We're going to store it in a mountain in Nevada. Because it not only needs to be stored, it also needs to be monitored, right? So this is a big issue with nuclear energy. Okay, now, other ones, here's this radon 220. This is really fast half-life. Carbon 14, we're going to talk about this one. This is a beta decay, 5,700 years. We're going to talk about this one mostly today, this carbon 14. Okay, so here's just an example of, again, this is, if you remember what a first order reaction is with kinetics, right? It has this shape to it, right? And this is the percent original in our half-life. And so at every half-life, so here's when we have 100% initial, we have 100%. After one half-life, only 50% of it is there. So if this was carbon 14, 5,730 years, so it would take 5,730 years to get it to one half-life. Now half of 50 is about 25. So it would take another 5,730 years till it has 25% left. Half of that is like 12.5. It would take another 5,730 years, and then there's about 12.5% of it left, and then exponentially, right? It's like limits, never actually gets to zero, but it approaches zero. And so that's the idea of half-lives. And so again, half the radioactive atoms decay after each half-life. So half of it is gone. So here's radon 220. Again, this one's quite fast. This one, this is 10 minutes, right? Some of them are a billion. So the amount of radon in atoms, you can see, decreases quite quickly at each half-life. So this just divides in two. Here is gold 198. Its half-life is 2.7 days. So you can see each of these half-lives, they have the exact same curve. No matter how long the half-life is, the curve looks exactly the same because it's a first order. It's a first order when we're talking about our kinetics with our rate laws. Okay, so let's practice this. So if you have 1.3 milligram sample, so that's the amount we have, of Pu-236, calculate the mass that will remain after 5 years. And the half-life is 2.86 years. So we want to know how much is left, how much will remain after 5 years. So a few things we need to figure out. We need to figure out our rate constant. We need to find our K. And then after we find our K, then we can figure out the amount that's left. So there's two equations. These are the same two equations I just showed you. So now we just need to use these. So our half-life is 2.86 years. So we're going to plug in our half-life here, and I don't care how you want to solve this piece of it, whatever makes you happy here. So you have 2.86 years equals 0.693 divided by k, and solve for your k. Right, so however, I just tend to, instead of do that, I just remember it the other way. So k is 0.693 over my half-life. So 0.693 over my half-life, which is 2.86 years. Now, something you need to be careful about here. See here. These all need to be in the same. So if this is years, this has to be years. Right, so it's really whatever your half-life is. This might be seconds, it might be, you're going to see some crazy ones in a few minutes, but the units need to be the same, right? So that's an important piece. They need to be the same time. And same with the amounts, milligrams. You can't have 1 in grams and 1 in milligrams and 1 in atoms. Both milligrams, both grams, or both atoms. Just careful with your units on these. Okay, so when you do that, you get 0.242 years to the -1, right? Or some people don't like it, so 1 over years is fine too. So that's our K. So now what we're going to do is we're going to plug our K in, right? We have our original amount. So our original amount is 1.35. We have our K. We want to know our time, 5 years. We just need to solve for how much is left after 5 years. Okay, so there's our half-life. That's the same thing I did pretty much to the T. So now we need to plug in all of these numbers. So we have our natural log. Natural log. And remember, oh, we have this. We want to know how much remains. Sorry, I said something. I said it backwards there. Let me fix this. Let me just make sure I put that to the right one. And then now our K, we know this is our K, right? Okay, I'm gonna have to erase that piece. Okay, so when we do this, we need to use our equation. I think I have everything pointing to the right place. So natural log, I'm gonna try to write this as nice as I can, of at some time, we don't know how much we're gonna have after 5 years. I'll make sure my math ends up looking right when I do this. So it's NT over, right? We have our amount, which is 1.35. That's our NO. This is milligrams, sorry. That equals our negative K, negative 0.2423. I'm going to leave off my units, okay? This is to make it, actually, I'll leave them in there. I'm trying to write this as neatly as I can. Times our time, which is 5 years. So you can see years and years, they are going to cross off. Now, however you want to solve this, I like to just raise each side, right? In your calculator, second function natural log is the E button, not that button, that button, right? Little e, it should be second function ln in your calculator. So if you want to, you can just raise both sides, e to that, right? E to this makes this go away. NT over 1.35. I can just get rid of that. There you are. Equals e to the negative 0.2423 times 5, right? And then times 1.35. I'm only doing this math this one time. Usually I don't do the math for you, but I want to make sure everybody sees how I'm doing this math because I'm just going to fly through it next time. So cross, cross. So you see you get N. Here's my suggestion if you're like, oh, I don't know what you're doing with my math, which I'm sure most of you are totally fine with it. But if you're not, learn this formula. This is N at time 0, e to the negative kt. That's what I just rearranged, right? So if you want how much is left over some time, this is the equation you're going to use, right? And again, you just saw I just rearranged it for you. Okay. I don't know what you get. I'm sure I have this all here. Okay, so I'm going to erase that because I know you won't be able to see it. And you get 0.042 milligrams. I'm hoping this math is simple, like at least in the back of your head because you did it in 219, right? So you did this in kinetics. You just might not remember. Okay, so we started with 1.35. After 5 years, which if you think about it, it's about 2 half-lives, right? 5 years is about 2 half-lives. So we should have half of 1.35, half of 1.35. So if you take 1.35 divided by 2, and then divide it again by 2, you get 0.33, pretty close, 0.4. You can kind of already estimate what you were going to get. Okay, so we got 0.402 milligrams. Okay, how about you try this one? So radon 222 is a gas that is suspected, it's not suspected, they know it causes lung cancer as it leaks into houses. It's produced by the uranium decay, just like we talked about. Assuming no loss or gain from leakage, if there's 10.24 grams of radon 222 in the house today, how much radon will there be in 5.4 weeks? Assuming you never open your doors and your house is completely isolated from the world. And the half-life of radon 222 is 3.8 days. Okay, I want you to try this one. Same exact procedure we just went through. And then type your answer in the chat or circle it on your paper and we'll go through it in just a couple minutes. All right, let's try this. So gotta find our K and then plug it in. So here's I just put everything here that we need, right? So we gotta find our half-life of our K, and then we have both of these equations, right? And again, you can also do this one. NT equals NO to the E negative KT. That's just the rearranging of the equation if you don't want to rearrange it. Okay, so and then this one again, if you just want to remember this one, K is 0.69, just make that neater, 0.693 over the half-life. So these two are the same equations, just rearranged. If you're like, I don't want to rearrange it, then don't memorize it. I'm going to be giving you the ones in black, not the ones in red, so, but feel free. Whichever you want. So you get 0.182 inverse days. Now, I want you to see here, this is in days, right? The half-life they gave us in days, but the time was in weeks. We need these both in the same unit. I always change it to the unit of half-life. That's just what I do. So I'm going to make sure to change this weeks into days. They just need to be the same unit. What unit? Doesn't matter. They just have to be the same. Right? So 7 days in a week, right? So 5.4 weeks. Do a little conversion. 5.4 weeks, right? 1 week, 7 days. Whatever you get, right? Oh, look, out of it here. 37.8 days, right? So 37.8 days. 37.8 days. So then we just plug it in, and I'm just going to do this one. So at time t, I had 10.24 grams, right? Times e to the negative k, 0.182, 1 over days, times 37.8 days. All right, so we just see what we get. We get 0.011 grams left. And then our days cross out. And so if we look this after, so if our half-life is 3.8 days, like 4 days, 5 weeks, that's like 10 half-lives. So if you divided your amount by 10, that makes sense, right? 10 divided by 10 divided by 10 divided by 10, right, would be about 0.1 grams. So it makes sense. Okay, so that's how we do our half-lives using our first order rate reactions from kinetics that we learned last semester. Now, radiometric dating. So we're going to use that now, that exact form, to actually talk about radiometric dating. How do we figure out how old are things based on the degradation of the radioisotopes? So the nuclide, right, is going to degrade a specific time, and we're going to use that to date things. We're going to measure and compare the parent radioactive isotope and the stable daughter isotope to figure out the age of an object. So we're going to talk mostly about carbon dating, but in geological dating, they use uranium-238 to 206. Remember the one I told you was a billion years? Or they'll use KR40 to AR40, which that half-life, again, is a billion years. And because the Earth is between 4 and 4.5 billion, these two pathways are exactly the right timing, the right amount, or the half-life is the right time to actually age artifacts that are very, very old. And so if you have things that they say like, oh, this is 2 billion years, they probably use this one or this one. This one's probably a little bit more popular, but they use one of these two. But we are going to talk about radiocarbon dating because that's one you've probably heard about a lot more. So we know that all things that are alive or were once alive contain carbon, right? Because if you breathe in, you're taking in CO2, your body's assimilating CO2, right? And so there's 3 isotopes in nature, right? We have carbon 12, 13, and 14. Carbon 14 is the one that's radioactive. Its half-life is 5,730 years, or 5730, it's just how I remember it. And so you would think that this would have disappeared a long time ago, but it continues to be remade. And so I'm going to show you how it gets remade through this really adorable little picture. Okay, so you'd think 5,030 years, the Earth is 4.5 billion years old. How do we still have carbon-14 in our world? Well, here's how we have it. Carbon-14 is produced when atmospheric nitrogen is bombarded by cosmic rays. And so you can see, here's our atmospheric nitrogen. It gets bombarded and it makes carbon-14. Right? And just enough carbon-14 decays back into nitrogen after a long time. But what we're going to measure is, so how carbon dating works is, so there's a consistent amount of this is consistent and predictable, right? And so when something is living, right, it's continually uptaking this carbon-14, right? But when it dies, it's no longer uptaking carbon-14. The amount of carbon-12, so the majority of carbon is carbon-12, like 0.04% or something is carbon-14. It's like barely any is carbon-14. So the carbon-12 is never going to degrade. It's always going to be carbon-12 forever and ever, forever to infinity, it's carbon-12. But the carbon-14 will begin to degrade, right? Because it undergoes beta degradation. And so when that happens, so when something's alive, this ratio is constant. But when something dies, the ratio changes because this doesn't change, but this begins to decrease over time. And that's how radiometric carbon dating works. It literally is dating, it dates anything that was alive at one time. And you're going to see it has to be because of the half-life is about 5,000 years. It can't be more than 50,000 years old, or there's not enough carbon-14 left to actually date. All you can do is say it's older than, but you can't actually have an accurate date to it. So again, carbon-14 to carbon-12, that ratio is constant while things are living, right? But once it dies, the ratio begins to decrease. And so what they do in carbon dating is they measure the decrease in that ratio. They can tell how long an organism was alive or how long ago it was alive. And so again, 50,000 years is kind of the max because after that many half-lives, the amount left is so little. All you can say is older than 50,000. So for example, here's what I'm talking about. Right. So if you're going to look at the amount of carbon-14, so here's one, all of it is there. There's your first half-life, right? There's your first half-life right there, 5730 years. But if you go down here, look down here. So 1% of carbon's 38,000. There's 1% left. Can't go too much further with your half-lives, right? Okay, so let's practice this. So now, this is how I'm going to use the numbers they actually use in carbon dating to show you that it's the exact same thing we just did. They just have different units. Again, units are important as long as they're the same. So an ancient skull gives 4.5 disintegrations per minute gram carbon. If the living organisms gives 15.3 disintegrations per minute of grams carbon, how old is the skull? Okay, so here is the data they're giving us about how much is there. And they want to know how old. So how many years old is it, right? We want the time. So no matter what, we still have to figure out our rate constant. But this time they're telling us something about our half-lives, right? So it's just a little bit different. It's the exact, pretty much the same time, the same thing. It's just this time we have the rate. So this looks more like what you saw in Chem 219. It's basically the exact same equation. We just changed the, instead of milligrams or grams, we just changed it to this very interesting unit here. So again, if we want to know our rate constant, K is 0.693 over our half-life, right? And so 0.693 over the half-life of carbon-14 is 5,730 years. So that gives you, put a 0 there, 1.21 times 10 to the negative 4 inverse years, or 1 over years, however it makes you happy. And then we're going to plug this in and figure out just how old is this. Okay, so, oh, I already have that there for you. Okay, well, let me just show you that one so it's prettier, and then we'll do the next one. Okay, so now with this next one, what we're solving for, so, whoops. So before we were solving for this, this was our NT. Before, remember, it was NT over NO. We were solving for our NT. This time we're actually solving for the time. So they're giving us this, we're solving for T, right? So again, however you want to solve this is fine. If we plug this in, so the natural log is going to be at some time, so now, at some time, T. Trying to think of 1 or T, we're just going to leave it T versus initial. So this is going to be 4.50 over, so at some time, I don't know at what time, it gave off this. Now, it's this. Equals K 1.21 times 10 to the negative 4th, 1 over years, times T. And this is obviously going to be in years. So however you want to solve this, so natural log, so 4.5 divided by 15.3, I don't like, so I get natural log of 0.294. Natural log, oh, I forgot the negative here. And then, so this is 0. Sorry, we got 1.22 equals negative 1.21 times 10 to the negative 4 times T. So just divide this by 1.2 times 10 to the negative 4. Divided by 1.2 times 10 to the negative 4. I have 1.02 times 10 to the 4 years. 10 to the 4 years. Okay, so, and I have it solved here, I can see it. Oh, so much prettier. There it is. Now, this isn't exactly what I did. I mean, it is the same thing, I just solved it a little bit differently. But I want to draw your attention to common mistakes with your calculator with this one. The half-life, right? If you look at the distance, the amount here, right? You should not be getting a negative exponent, right? It's got to be greater than 1. It has to be more than 1 year, right? It's the time in year. So you should make sure that when you're doing this, if you're ever getting a negative exponent, something has gone wrong with carbon dating, right? So you should always have a positive exponent because the half-life is 5,730 years. If you look here, the difference here, 15 to 4.5, this is more than 1 half-life. Should be more than 5,000 years, right? That would only make sense. 15 to 4.5, definitely more than 1 half-life. Your answer should be bigger than 5,000, right? So you can draw some like slight conclusions when you're doing these. But again, never have a negative exponent. and you can kind of judge, you can't really judge exactly where your answer should be, but you can kind of get close. All right, so I'm gonna let you try this one. This is really fun. So an archaeologist have dated a civilization to 5,600 years ago. If a sample gives 20 counts per minute per gram carbon, what would be the number of counts per minute per gram carbon for the rice grain found at the site? So this time they're giving us T, and they're finding at some time T, the rate at some time T is 20 counts. And they want what was the rate at the site, okay? Sorry, this is rate, initial, and at the site. Okay, so I'm gonna give you a couple minutes to try and figure this one out. Very similar to what we did. And then we're gonna go over it together in just a couple minutes. Okay, it looks like some people are stuck on this one. So let's go over this one. So we have 20 crowns per minute per gram, and it's 15,600 years ago, which I'm just going to put all that in here, okay? This is what they give us. And I told you rate 0 was 20 counts. We want to know rate T, right? At rate T, what do we have? So same exact equations. It's always these two equations, right? These are our two equations when we're doing a first order rate law, period. These are our two equations. We're looking for this one this time. Right? Last time we were looking for T, this time they gave us T, we're just looking for the rate at that time, right, at time T. Okay. We find our K, I figure you're good at finding your K now, right? Here's our K. The K, by the way, it's always the same because radiocarbon dating is always the same half-life. So this K is the same. I mean, I would memorize it because you can just divide it, but the K is always the same. And then all we're gonna do is we're gonna plug it in and we're just solving for rate T. So very similar to what we did before. Here's our negative K and there's our time. Again, they're both in years. We are both in years. And then this is counts per minute per gram, counts per minute grams carbon, counts per minute grams carbon. Now this one's a little harder to predict because the unit is odd and it's gonna seem weird to you. But if you think about it, This is 5,600 years, which is approximately like 3 half-lives. So it should be 20 divided by 2, which is 10, divided by 2, which is 5. 5, 3. I mean, using your mental math, I mean, it's pretty close, right? Now, I'm going to show you using radiocarbon dating. If something is, and this is, by the way, this is what they can tell. This is, I'll show you how they do this using the chart. So if something is 15, so we decided it was 15,600 years ago. Here's a little chart. So 15,600 years ago means this is about how much carbon 14 you should have in there, right? If we look at how much carbon 14, right, about 25% of the original. That makes sense, right? About and about and around. So 15,000 years is right in here. In between 10 and 25%. Makes sense, right? So there's a little bit of logic to it. Again, it's all kind of new to us, but there's a little bit more logic to it. Okay, so that's all the kinetics I'll do for you today. No more kinetics. So we're going to talk just briefly about nuclear fission versus, we'll talk more about fusion tomorrow and on Monday. But fission, again, is the splitting of a nucleus. Fusion is the joining together of nuclei, right? Or they would say smashing together of nuclei. So we're going to talk about fission today. Both fission and fusion release enormous amounts of energy. Fusion much more than fission. But fusion needs the temperature of the sun, which is kind of hard to do. Fission does not. So what do we do with fission? So fission, we're going to specifically talk about uranium-238 because this is the same fission that they do in nuclear energy. So what they do is they take a high energy neutron and they shoot it at the nucleus of uranium-238, right? So here's an atom plus a neutron. This nucleus is going to split into 2 smaller pieces. When it does that, it releases lots and lots of energy and, coincidentally, 3 more high energy neutrons, which guess what they're going to do? Find more uranium-238. So this is kind of the backbone of what fission in a nuclear reactor does. So a chain reaction is what occurs when the neutrons, the 3 neutrons, hit 3 more nuclei, which then release neutrons, which then hit more, right? So it's kind of like they keep going and keep going and keep going. So many of the neutrons that are produced in fission are either ejected from the uranium before they hit another uranium-235, or they're absorbed by other 238. In some, we're going to talk about where they go. The minimum amount of fissionable isotopes. Now, we'll talk about that in just a second. Needed to sustain a chain reaction is called the critical mass. So I liken it to, think of uranium-238, which is the one that is unstable and that you can fission, which means split. Think if you had an entire room filled with mousetraps. Have you ever seen this on YouTube? If you haven't, it's pretty cool. I need to put it in the lecture. And if you took a ball, right, like if you had a golf ball and you like hit it on one, all of a sudden they start popping everywhere and like all the mousetraps go off, right? That's like a chain reaction. Now, if you only had 6 mousetraps in a room and you threw a ball in, maybe 1 or 2 of them would I guess catch, or whatever that's called. So a critical mass is the minimum amount for the reaction to keep going without you having to do anything else. So that's what I mean by a critical mass. And so here's kind of an example of what happens at the very beginning of what we would call a chain reaction. So you need enough for every time you release these 3, you need to hit another uranium-235. I think I said 238 at once, 235, and then it splits, and then these hit another 3 nuclei, right? Which then release another 3 uranium, which hit another 3 nuclei, and so on and so on and so on and so on. And so you have to have enough uranium for that to occur. That's a chain reaction. So the fissionable isotope, yeah, I think I said 238 before. I meant 235. I'm pretty sure I said it incorrectly. The ones that we're just going to talk about is uranium. These are also fissionable isotopes. So now, uranium in the ground, 1% uranium-235, and the rest is 238. Not enough to sustain a chain reaction. Now, a lot of times people, one of the big fears of nuclear chemistry is like, it's going to blow up, it's going to make a nuclear explosion. It's not possible. The reason it's not possible is because there's not enough enriched uranium. So if you remember, I mean, it's still a pretty big deal, but even a couple years ago, there was like the Iran nuclear deal. And the whole issue with the Iran nuclear deal is Iran was enriching uranium. And they were saying they were enriching uranium for their reactor. And for the reactor, well, you only need about 3% uranium, 235 to 238, for your nuclear reactor. Once you're going to 3 to 5 to 7, now it's weapons grade, right? And it is incredibly difficult to do this. You take some seriously precise equipment to be able to do that. Because remember, the only difference between uranium-238 and uranium-235 is the mass of 3 neutrons. A neutron's like 1 to the minus 24 grams. Okay, think of how you separate your liquids in class. Use a centrifuge, right? That's how you separate your precipitate, right? Because the precipitate is heavier than the solution, and so it falls to the bottom. Same thing, uranium-238, think of the centrifuge you need to separate something that's 1 to the 24th grams. Very expensive, very precise equipment. The hardest part of making a nuclear bomb is separating 235 to 238. And so the whole issue with Iranian, the nuclear deal here, is they don't want them enriching uranium because they don't want them to go from reactor grade to weapons grade. Iran keeps saying, we're just going to reactor grade, and they won't let anybody in to check and see if they're actually going to weapons grade. So there you are. There's your political science lesson for the day in chemistry. Okay, so now, another issue with nuclear fuel is once it gets like about 1.5, or this is kind of like the minimum, usually even a little bit higher than that, it can't sustain a nuclear reaction, which means now we have a spent fuel, and now we have fuel that has uranium in it, but we can't use it because it doesn't have enough uranium to sustain a nuclear reaction. So then we need to go store it for 1 billion years. Right? So what some countries do is they buy that spent fuel and then they try to enrich it back up to 3%. Again, very difficult, very hard to do, very expensive. So now why, with all, I keep telling you all the problems of nuclear energy so far, why do we use it? Okay, here's why we use it. So we use about 50 kilograms of fuel to generate enough electricity for 1 million people. Right? It has no air pollution, right? So if you had a coal burning versus uranium fuel, so uranium uses about 50 kilograms, has no air pollution. Coal, 2 million tons. Okay, so you're like, these amounts don't mean a lot to you. Okay, think of this. A semi-truck full of coal from the brim, full to the bottom of coal. The same amount of energy that you would need for uranium is about that much. It's like the top of your pencil, like a pencil eraser, right? That same amount. So an entire semi-truck or like a pencil eraser, right? So you need not very much uranium, and you create the same amount of energy. You also have no air pollution when it comes to nuclear energy, but coal produces, we call this nitrogen dioxide and SOx, NOx and SOx, which creates acid rain. This one creates this kind of acid rain. This is West Coast acid rain, and this is East Coast acid rain. Both create acid rain. We create nitric acid over here. They create sulfuric acid over here, right? And it also produces tons and tons and tons of CO2, right? And CO2 is very, very bad for global warming and climate change because it's trapping heat in the atmosphere. Okay, so I think we'll stop there, and then